Last time, we've shown why we need a link budget for the analysis of eye height and eye width respectively. But in this video, I will show the image of why we need a thorough two-dimensional link budget in a gray PPA wireline SerDes. By the way, the PPA stands for power, performance, and area in a wireline SerDes. Let's start with the poor PPA, which means high power, low performance, and a big area in a SerDes design from system to circuit block. For example, first thing first, in the high power mode, what does that imply? Think about the critical power images for 3 seconds. Yes, the TX output swing would be maxima. Second, what does low performance imply? Think about the transmission data or media images for 3 seconds. Correct. The data rate or speed would be minimized, or the media loss would also be minimized. The last one is the high secant area tolerance. What does big area imply? Think about the most area consuming images of the passive elements for 3 seconds. Bingo! Bigger capacitance, more decoupling capacitance would decrease the supply ground noise, and more filtering capacitance would decrease the thermal noise by simply imaging the KT on C noise. So, what's the eye diagram at the sampler input should look like if there's only residual RSI? Think about a big open eye images for 5 seconds. Correct. You can see the eye of the residual RSI after CTOE only equation is wide open, like a square wave. Is that still wide open after adding all the RJ from the TX all the way to the RX data path and its clock path in the eye width? Think about the jitter budget of the eye width for 5 seconds. Bingo! The eye width should shrink after adding the 0.5% UI of the RMS-RJ and 0.5% UI of the extra DJ. What's the eye width left or peak-to-peak jitter? Right, you should be able to evaluate the peak-to-peak jitter for bit array 1E-12 to be 10% UI from the link budget of the eye width exercise. What's the next one? Right, the next one will be the link budget of the eye height if adding 10 mV RMS thermal noise to the RX data path from the CTOE, preamplifier, and sampler. Therefore, the eye height will reduce by 140 mV, 70 mV per side from the residual only eye height. From the link budget of both eye width and eye height, we add the random jitter RJ and the normal distribution voltage noise Vn respectively. Then we see the effect on both simulations match the hand calculation from our previous 2 link budget videos. What happens if we add both RJ and Vn at the same time? Think about the slew rate images for 5 seconds. Correct. The slew rate of the transition time is very fast. Therefore, the sharp slope would have much less amplitude to jitter or jitter to amplitude interaction. An image is more than 1,000 words. You can tell that the eye width of the RJ and Vn is almost the same as the eye width of RJ only, and the eye height of the RJ and RVN is almost the same as the eye height of the Vn only. Therefore, our previous estimation of the 2 link budget videos should apply to their poor PPA well enough. How about the gray PPA? First of all, we need to understand the gray PPA means low power, high performance, and low area in a SerDes design from system to circuit blocks. Therefore, just apply any opposite items from the poor PPA to make it simple. For example, first, in the low power mode, the TX output swing would be reduced as small as possible. Second, high performance implies a maximum data rate in a high channel loss. Third, a low signal area implies less decoupling capacitance and filtering capacitance. So both SI and PI will shrink the eye opening further. Then what's the eye diagram at the sampler input should look like if there's only residual ISI for the gray PPA link? Think about small and smooth eye images for 5 seconds. Right, you can see the eye of the residual ISI only after the TXFFE, IXCTOE, and IXDFE equation is wide open. But it's not an eye of a square shape anymore. Instead, it's an eye of a diamond shape. Is it still possible to keep a wide open eye after adding all the RJ? Think about the jitter budget eye width for 5 seconds. Bingo! Yes or no? Since the residual ISI only eye width is 80% UI and extra 1% UI of the IMS, RJ, and DJ would degrade the eye width to 65% UI, which could be still big enough. But that's not accurate without considering the vertical thermal noise. So think about the link budget of the eye high image for 5 seconds. Correct. In addition to the eye high of the residual ISI only, adding the 5 millivolt IMS thermal noise at the RX data path, the eye would degrade to 170 millivolt from 240 millivolt for the BL rate equals 1E-12, which matches to our hand calculation from our link budget video of the eye high. But again, is that still accurate if we add both RJ and VN together? Think about the slew image one more time for 5 seconds. Right, after 5 seconds of thinking, just look at the inner eye opening in your eye. Is the final eye with RJ and VN the same as the eye with RJ only or the eye with VN only? Of course not, due to the slow slew rate and the data transition of the diamond-shaped eye. Both vertical voltage and horizontal jitter will interact with each other. Therefore, to get an accurate eye width or eye height, the separate link budget is not precise enough. What can we do? Bingo! Simply by moving the eye of the residual ISI only, eye width equals 80% UI and eye height equals 240 millivolt up and down by 35 millivolt for BL rate equals 1E-12, and then moving it left and left by 7 or 8% UI, then the final eye will be very close to the eye width 50% UI and eye height 150 millivolt, which matches simulation 1. Therefore, this link budget of the 2D eye will be more precise for the gray PPA C-link. Here is the summarized image of why we need a thorough 2-dimensional link budget in a gray PPA wireline SerDes. We started with the opposite pool PPA SerDes. The square-shaped eye may decouple the eye width and the eye height nicely. Therefore, our previous 2 link budget videos for the eye width and eye height respectively would apply well enough. But in a gray PPA SerDes, the shape is almost diamond, which would correlate both eye width and eye height tightly due to the slow data transition or small slew rate. Therefore, we must move the eye of the residual ISI only up and down by thermal noise voltage outlier under the target BL rate, then move it left and right by random jitter outlier as well. The exercise image shows the resulting eye is precise enough compared to the eye from the system simulation. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.